Hello, today we are going to do Paul Hewitt's Conceptual Physics, Chapter 20, on gases. Okay. Gases. I hate that we don't double the S anymore. Just gonna do it anyway. Okay, so gas is a fluid. So remember, if we look at liquids, in solids, we have things in very even crystal form. In liquids, everything is just sort of, tumbling over each other, but virtually not compressible because they're all jammed in. And then we look at gases and they're far apart, okay? So like gases, so this is liquid. This is, the crystal structure of, this is a solid, this is a gas. So you can see that solids, are in a crystal form. Liquids and gases are both fluids. So that's what we're looking at right now, is fluids. But you'll see the main difference between liquid and gas is you can notice gas, the molecules are much farther apart, and therefore they're much, it varies a lot. They're much farther apart. They're a lot less dense, but the main difference, these are all fluid, liquids and gases are both fluids, but you'll see the main difference is that gas is actually compressible. And this changes. In a lot of ways, gases act like liquids, but in some things they're different, and that's because it's actually compressible. Liquids are virtually uncompressible. Gases are compressible. So remember we talked about how we live at the bottom of an ocean of gas. And gas has they're a lot farther apart, but gas has real weight to it. We don't feel it for the same reason, like if someone handed you a bag of air, you wouldn't feel the weight of it for the same reason that if you were in a pool, and someone handed you a bag of water, you don't feel it. Where if you're in air and someone handed you a bag of water, you'd feel it. It's kind of similar to that. But anyways, we live at the bottom of this ocean of gas. And because it's compressible, when we're down at the bottom of this ocean of gas, if you're up on a mountain, or if you're down in the valley, the air molecules are actually pushed closer together by gravity. Down in the valley, they're further apart up in the mountaintop. And you'll notice this if you go from when you go visit the Rocky Mountains, and suppose you live near sea level, and you go up to a high mountaintop, you will notice that the air is thinner because you'll notice that you feel out of breath, that you need to take more breaths to get the same amount of oxygen. That's because air is thinner, so every breath you're actually getting less oxygen. This is why athletes often will go to mountains to train, because as you feel out of breath and you adjust, how you adjust is your body's actually putting in more hemoglobin, more to capture the oxygen. So your body actually gets better at capturing the oxygen. And then if you go back down to the valley with the denser oxygen, you suddenly have an advantage over everyone who is just training in the valley. If you go and train on the mountain, yes.
Are we in a valley?
I think we're not a very high altitude, but I can't 100% remember what our altitude is.
Okay.
But you can feel the difference when we go from here to the Rocky Mountains.
Oh yeah, and Mom, when we went to Minkus Mountain, all our marshmallows got fluffy,
yes.
And they taste better.
Yes. Marshmallows are fluffier when you go to the mountains, because marshmallows have captured pockets of air in them. So if you take the same marshmallow and you go down to the Dead Sea Valley, you're gonna have a little dense marshmallow. And if you go up to Mount Everest, you'll have a puffy marshmallow, because all those little pockets of air in the marshmallow will expand. Okay, so you might say, well, what is the density of air? So at where we are now, like regular sea level, the density of air is 1.2 kilograms per cubic meter. Okay, so in about this much space, this much space, and a cubic meter is holding about 1.2 kilograms of matter. And for translate that to pounds, that's somewhere around almost 3 pounds. Between 2 and 3 pounds of. Wait, I'm almost done. Between 2 and 3 pounds of oxygen or of air molecules is in a cubic meter. Okay, so yeah, we would bloat in space. If one of the many bad things that would happen to you if you went out into space without a spacesuit, you would kind of puff up. All the liquids in you would start boiling, because boiling point has to do with air pressure, and various things would happen.
That does not sound right.
But we are slightly compressed more by living in the bottom of this ocean of air. Okay, so we're going to talk a little bit about straws. Okay, so when you are drinking, all right, let's go back to barometers. So barometers are how people measure, and the book goes into detail between the difference between like these mercury, I think, barometers, and then these not using a liquid barometer. Barometers measure the air pressure. Another way of thinking about a barometer is those, when we talk about the marshmallows, chip bags. I noticed when we were in I can't remember where we were, I was somewhere low elevation, and there was the bags of Doritos at the grocery store, and they had these kind of sad, kind of half deflated, I mean, like no one opened the bag yet, but they look kind of pathetic, like the Dorito bag is sort of half crumpled looking, not very appealing. When we were up in the Rocky Mountains, those same bags of Doritos were puffy. They looked very appealing, puffy, like a balloon, and like a Mylar balloon. And the reason is because when they bag those chips at the factory, they know that when you take that bag up, where the air pressure is less, when you take it up to the Rocky Mountains, the air inside will push more. And so the same bag of chips that looks sad and deflated at the bottom of the mountain will look big and puffy at the top. And that is why I used to wonder, why don't they fill up the chip bags all to look beautiful and puffy? If you had a big puffy chip bag and then your trucker drove up a mountain, all your chip bags would pop. So think about that. Next time you are like in the mountains or something, go to a vending machine and look at the chip bags. Or even better, if you can take that chip bag with you and then drive to the bottom of the mountain and you can see the same chip bag change. That chip bag is a barometer. It is showing you the pressure of the air pressure changes. Because remember, the chip bag has the same amount of gas molecules or air molecules inside it when it's sealed. And so as you go up, they expand in that puffy chip bag. Down, it's more compressed, crumpled chip bag, as long as it's not opened. Okay, so let's talk a little bit about straws. So when you drink from a straw is also like a barometer. It has to do with pressure. When you drink from a straw, you're not actually truly sucking the liquid up. What you're actually doing, so this is your cup, okay, and then this is your liquid. Shh, wait, no, not yet. Liquid, this is your liquid in your cup. And then you've got the straw. You're sucking on it. What's actually going is that with your mouth, you're creating a vacuum. You're sucking the air molecules out of this part of the straw. And what happens is then when you create a vacuum here, remember there are air molecules, okay, around your drink. So what happens here then is that the air pressure will push, because all of a sudden there's a vacuum here. It's not balanced. Before you sucked the straw, there were air molecules in the straw too, right? They're all pushing down on the liquid the same. When you suck those air molecules out and create a vacuum in your straw, these air molecules are still pushing. So what happens when they're pushing here and nothing's pushing here? The liquid goes up to your mouth. So when you're sucking from a straw, what's actually going on is you're creating a little vacuum, and the air pressure is pushing the liquid up into your mouth. Can you get a cough drop, sweetie? I did some hot tea. So there's actually a limit, because remember, we only have a certain amount of air pressure. At sea level, that limit is about 30 feet. So even if your mouth is replaced with a super cool vacuum pump, it will only be able to push that straw up 30 feet. If you've got higher than 30 feet, or ish, what's the estimate? If it's higher than 30 feet, even the best vacuum pump in the world can't suck it up any farther. And that's because we're really depending on the pressure pushing this, and this air pressure is set by how much the air pressure actually is. So if you went to somewhere like Jupiter, if you could actually be on this floating station, whatever. If you went to a more massive planet where the gravity is stronger and the air pressure is stronger, if you went there, then you could suck something up with a taller straw. But on Earth at sea level, the straw kind of maxes out, or vacuum pumps, I should say, max out. Vacuum pump is doing what your mouth does, but even better, at around 30 feet. I think they said it was like 10 point something meters. Okay, so now we're going to talk about the buoyancy of air. So in the same way that water, water gives you buoyancy that we talked about in last lecture, air pushes you up too. That's how hot air balloons work. You see a hot air balloon and it's floating up. It is floating up by the weight of the air that it is displacing. it's the same way, or the dirigibles, the big, you know, the funny looking dirigibles that you see looking like this or something, they're doing the same thing. I think, wasn't there a famous dirigible, I cannot think of the name of it right now, and they filled it up with, I think it was hydrogen gas, because hydrogen gas is even more fluffy. I mean, remember, it's only got one, atomic number is 1, it's only got one little proton or neutron or whatnot. Hydrogen is even more fluffy than helium gas, and so, you know, it works even better, and so they filled their dirigible with hydrogen gas, which is very flammable. I think it went down in flames and made newspaper headlines, and it was a really big deal. This was a long time ago, like 100 years ago or something. But anyways, hot air balloons work by, they heat the air, and then the air expands because it's hotter. So now you have less, now that you've got heated air, you've got less dense, you know, if around it, the air's like this. And then you heat it with your little flame in here. Now you've got less dense air, and so it goes up. Because remember, this is less dense than the surrounding area. It's like that beach ball. Than the surrounding sea of air, and it will go up. Okay. So we're going to talk a little bit. Sweetie, please get a cup of hot tea. Okay?
Got it.
We'll get a cup of hot tea. All right. So now we're going to talk about Bernoulli's principle. So Bernoulli's principle is how airplanes work. And to be honest, it sounded so fantastical to me when I learned about it in high school that I didn't really believe it. But I rode on a plane. And I stared out the window, and I did some experiments with the pool water, the jets that come in a pool. So Bernoulli's principle is really bizarre, and it's that basically when you have a moving fluid, it's lower pressure than the surrounding liquid. As long as that fluid is moving in a nice straight line, I think they call it laminar flow, as long as it's moving in a nice straight line, it's actually lower pressure here than the air around it. And because of that, well, we'll get to airplanes. So at first I didn't really believe this because it just sounds nuts. You just feel like if it's moving, the pressure should be greater. Now, explanation here, we're not saying the pressure here isn't greater than the not moving water, Obviously, if you stand here, you're going to feel it bam, 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 bam into you. That will be high pressure. We're talking about the pressure within that jet stream where you're hanging out in here. So I tried this experiment. I went to a swimming pool, and they had like those underwater jets that came in the sides. And I got my fingers up to that jet of water squirting through. And I thought, if this jet of water that's going to come through is actually lower pressure than the surrounding water, it will pinch my fingers together. The rest of the water will push my fingers together because this stream of straight flowing water will be lower pressure. And I did it, and it worked. It was so weird. I just kept going up to the jets. You stick your fingers and you feel them being pulled toward each other. This is why when you're driving on the highway and a giant semi truck goes really fast, barreling past you, you find yourself like being sucked toward them. Because what's happening is that semi truck, so this is a bird's eye view, that semi truck is sort of dragging the air along with it. And going really fast, so there's a gust of air going this way. You, the little car here, so all of a sudden there's a low pressure zone of air between you, and the surrounding air that's not moving as fast will push you in because it's lower pressure here, higher pressure here, and that is why you'll sort of get sucked toward that semi truck. You can feel it. You can especially feel it if you're riding shotgun in the back of a pickup truck at 70 miles an hour, which you should never, ever, ever do. Okay, so you can also test it out by, they often like to do these experiments with Bernoulli principle, so you get a, so you think if I blow on the paper, it'll blow the paper away, right? But what I'm actually doing is I'm producing, okay, you need to get in contact with my stream. I'm not doing a very good job. All right, I think it needs to be a strip of paper. But basically, if you get a strip of paper and you blow on it, and you will feel it pull up because the higher pressure air around it will push it into your stream, the same way that the car and that will go. Let me see if I can get this to work. I need a little strip of paper to do this right. Okay, so I've got a strip of paper here. Do you see how it comes up when I blow? You'd think it would be blowing the paper away. But what's happening is that as I'm blowing, that stream of air is lower pressure than the air underneath it. And the air underneath it is actually what's pushing it up. This is how airplanes fly. So what airplane does is they carefully, I used to think airplane wings should be beautiful and flat, like those early biplane wing things you see. But no, they want airplane wings that are curved at the top. That they look kind of like if you cut the airplane wing this way. Okay, we're looking at a chopped off airplane wing. Okay, this is the three-dimensional. I'm not doing a very good job, but you get the idea. This is a three-dimensional cross section of the airplane wing. And what ends up happening here is as it's as you put the jet engines going and it's moving forward, the air here is just doing that, but the air here has to go faster. Because the air here has to go faster because it's going over the wing. Because this air is moving much faster than this air. Look, this has to traverse more distance than this air. Because this is faster than this air, this becomes a slightly lower pressure than here. So then what happens? Since this is lower pressure, this higher pressure air pushes it up. And that's called lift. And it just sounds nuts. And I'm like, really? The curvature of that airplane wing is what is, and the weird Bernoulli's principle is what's putting this giant, massive craft of steel and whatnot into the sky. I remember getting a seat in an airplane next to the window and just staring at the airplane wing, and I just thought, there's no way this is going to work. Like, I know it's going to work, but in my head, it just feels like, really? Bernoulli's principle really does that? And it really does that. I mean, you guys know, air travel is a real thing. It's just really cool that the moving, now, this only applies, remember they said laminar flow, when things are moving in nice, smooth lines. If air starts, for whatever reason, doing these little eddy current, little swirls, if the air starts swirling, turbulence, Bernoulli's principle doesn't apply anymore. This is why, if you've ever been in an airplane and it starts like bumping around and they're like, we hit some turbulence, we're gonna be all right, everyone calm down, stay in your seats, don't get up. That's you hitting turbulence. And that's because all of a sudden the airplane lift isn't working as smoothly as it ought to be working, because you're hitting like pockets of, eddy, swirling currents of air, and you don't want that when you're in an airplane. That's what hitting turbulence means. Okay, and I think that is that everything. We covered Bernoulli's principle, airplane wings. Oh, fun fact, when winds blow a roof off, it's like this. When winds blow, using Bernoulli's principle, sometimes when you hear about people in high winds getting their roofs blown off, what happens is that the air is coming in high winds, and look, it's doing exactly what it's doing with the airplane. And then the pressure, the regular air, stagnant air inside the house, is all of a sudden high pressure compared to this. This is a low pressure, this is high pressure. So the own air, wait. Oh, give me one more minute, I'm almost done. The air, your air in your house, it's not actually the winds, the high winds that like tear your roof off. It's the air inside your house that pop the roof up because of the lift. Here, your roof is now acting like the airplane wing. Lower pressure, all that high pressure in the house, your roof gets popped up if it's a high enough winds. This is why they have roof vents, Audic vents or whatever. They have like little whole roof vents. They have these roof vents so in high wind times, the wind can, go through your house. It doesn't have all that stagnant air ready to pop the roof off when the winds are too high. Okay, I think we covered all of that. All right. All right.
Can I turn it on now?
Yeah, you can turn it on now.